take this square.
Okay, so a couple of things today. First of all, we're going to do some complex variable theory, and I'm going to try to get through a lot of material today because the semester is going by. Also, I've got a new policy here. You guys still like the crackers or not? I don't.
Yeah, crackers are good.
All right. But I also have some Halloween candy left over. And apparently the media have so spooked the parents in Albuquerque that hardly any kids came by this year and last year. So I've got maybe 2 pounds of candy. So the thing will be, anybody who asks a question gets a candy. That's to encourage questions. All right, last time the last topic was Cauchy's inequality. And what we did was, we said, suppose f of z, let me just review Cauchy's inequality, that f of z is analytic in some region R that includes some sort of a disk with perimeter z equals r e to the I theta. So in other words, the analytic region includes a circle of radius r about the origin. And f of z is less than or equal to m for z equal to r e to the I theta. So the analytic function f is bounded on the perimeter of the circle. So we've got a circle here, radius r. Okay, well, by using Cauchy's integral formula, which is that the nth derivative of z at 0, the center of the circle, is equal to n factorial over 2 pi I, an integral around the circle of f of z dz over z to the n plus 1, we can take the absolute value of that and get the inequality. The nth derivative at 0 is less than or equal to n factorial over 2 pi, an integral absolute value of f of z, let's see what I said here, dz over absolute value of z to the n plus 1, and now the absolute value of z is obviously equal to r. dz, as usual, is I r e to the I theta d theta, and so altogether this is less than or equal to n factorial over 2 pi. F is bounded by m, so we can pull out an m. So then this is an integral 0 to 2 pi d theta. There's an r up here, so this is r to the n. And that means that the nth derivative at 0 is then less than or equal to n factorial m over r to the n. The 2 pi's cancel with the integral over d theta, which is 2 pi. So that gives you an...
What do you mean you could pull out an m? I know it's bounded by m, but why were you able to pull m out of the
Oh, it's a
integral?
constant, so I just removed it from the integration.
Where was it in the
It's right here.
in f?
Actually, you're asking multiple questions.
What? It was a function of the variable it's bound by?
Well, f of z is less than or equal to m on the circle. So we can replace f of z by m and preserve the inequality.
Oh, okay.
So if any of you are hungry, or have friends who like chocolate, I don't particularly recommend eating a lot of chocolate, but I like eating a lot of candy, but of the candies, chocolate is probably the best one to use. At least that's what the manufacturers of chocolate does. Okay, so is that all right? By the way, a year ago when I brought in some chocolate and said that I'd give a piece to anybody who asked a question, one of the students immediately said, "What kind of chocolate?" Okay, the next one is one of Liouville's theorems. So Liouville's theorem. Now we're assuming that f of z is analytic everywhere. And that means another way of saying is that it's analytic everywhere is to say that it's entire. So entire is the same as everywhere analytic. I put the new homework assignment on the web. It's basically to do all the problems at the end of the chapter that we already finished in class. And we're saying that f of z is bounded by m for z greater than some r0. So there's some circle, and outside that circle, f of z is not only, it's analytic everywhere, but outside the circle of, say, radius r0, it's in fact bounded in absolute value by some number m. Well, that means that the conditions for Cauchy's inequality are satisfied, and consequently, the nth derivative f0 of this function is less than or equal to n factorial m over r0 to the n. But, of course, we could repeat this same statement here if it's for any r greater than r0, because if it's bounded by m for z in absolute value greater than r0, it's certainly also bounded by m for z greater than in absolute value than some r. And so what we then say is that f of n is less than or equal to n factorial of the same n over r to the n for all r greater than or equal to r0. Now we take the limit as r goes to infinity, and we have that fn of 0 is equal to 0. So that's the result of Liouville's theorem, namely that all the derivatives of the function f at 0 vanish identically. Questions? Okay. Now that means that we can set up a Taylor series, because all the conditions for Taylor series are set up and are valid. And so we can set up a Taylor series for f about 0. And so it's z to the n over n factorial fn of 0, the nth derivative at 0. And so that is nothing more than f of 0. So in other words, the function that satisfies Liouville's conditions has to be a constant. So in other words, any function that's entire and that is bounded outside some circle is a constant. Questions? Let me just say that I've got quite a supply here, so you can ask questions and I'll toss you a piece of candy.
I guess I could ask a semi-relevant question.
What's that?
Is it true that Cauchy opposed French Revolution was loyal to the king? I think.
Unfortunately, I don't know enough history to tell you that. But you could certainly wiki Cauchy and
I've heard that somewhere.
Cauchy and 1789, say, and see. I mean, just, of course, you know, well, no, I'm not going to speculate on French history. Okay. Now, Gauss applied Liouville's theorem to prove the fundamental theorem of algebra, which is something that we used back in chapter 1. And in fact, what he did was he said, suppose we have some polynomial of nth degree or order. In other words, Pn of z is, what shall we say? I see, I should have used the sum Cj z to the j, k equals 0 to capital N. Suppose that's a polynomial, okay? And the polynomial is entire, and so then f of z equals the 1 over, excuse me, Pn of z. Well, suppose this polynomial, now in fact let me tell you what the fundamental theorem of algebra is, remind you that a polynomial of nth order or nth degree, polynomial like this, has n zeros in the complex plane. That means then that the function f of z would have n singularities in the complex plane. Now they might be all at one point. The polynomial might be z to the n, in which case it's a pole of order n at 0. But in any event, there are these various singularities. And so what we're going to do is we're going to assume the contrary. We're going to assume that you can have a polynomial of nth order that has no zeros. Here, of course, we're talking about n greater than 1. If the polynomial is of order 0, it can have no zeros, because it's just a constant. All right, so this is what Gauss said. Well, in this case, f of z is entire. If p had no zeros, f of z would be entire. In other words, analytic everywhere. And moreover, for big Z, f of z could be bounded by something like 1 over the absolute value of Cn, absolute value of z to the n. Now I'm leaving out of terms of order.
Wait,
Yes.
didn't you say it only has no zeros for the trivial? I thought that was only the trivial case.
I'm working through this pretty fast. Oh. So say it again. What?
You're saying the polynomial is entire?
No, I'm saying f is entire. If the polynomial has no zeros, f of z is entire.
Isn't that only for the trivial case where it has no zeros?
Yes, but that's what we're trying to prove. So we're assuming that we're trying to prove that f of z and that p has n zeros, capital N zeros. We assume the contrary, has no zeros. We assume in fact the radical contrary, no zeros. Then f of z is entire. And moreover, for big Z, it's bounded by something like this. Now, it's an approximate bound. And which is to say 1 over C sub n r to the n, which I'm going to call m, for absolute value z greater than or equal to r. In fact, I can make it r0. So now this satisfies all the Liouville conditions. It's entire and it's bounded outside the circle of radius r0. Okay. But that would mean that f of z would be a constant by Liouville's theorem. So hence, f of z is just equal to a constant, which in this particular case would be z0. But obviously, if n is greater than 1, f of z, we don't know about the zeros yet, but it surely isn't a constant if it's a polynomial. So the only way out of the contradiction is to say that p has at least one 0. So then what you say is, if this is equal to z minus, and what did I call this? Z minus z1 times some other polynomial, pn minus 1 of z. Okay. So the next thing you do is you start over and you apply Gauss's reasoning to the polynomial pn minus 1 of z. You assume it has no zeros. You then take 1 over pn minus 1 of z. That's entire then, and that if pn minus 1 has no zeros, you then bound it, you apply Liouville's theorem, you get that it's a constant, but it can't be a constant unless capital N is 1. And in that case, you get to the conclusion that this is z minus z2 times p n minus 2 of z. Anyway, you continue in this way, and eventually you prove that p of z has n zeros somewhere in the complex point. And they might be all at one point, it might be 2 at one point, and 3 at another, and the rest distributed randomly. Okay, does anybody have a question? All right, so that's the fundamental theorem of algebra, and what that means then is, the conclusion is that Pn of z is some product, some constant Cn times the product j equals 1 to capital N z minus zj. So that's the form that every polynomial must take, where but the zj's are close to complex. All right, the next topic is what are called Laurent series. And these are the ones that sort of came up when I said that you can think of the Fourier series as kind of power series. Well, it's not really a power series anymore. It's either 2 power series or the Laurent series. All right, so to prove this, what we do is we draw a picture here, and we've got center of a circle z0, some point z, and then we draw 2 circles around this thing. There's one. Whoa. All right, I'm not tall enough to draw a perfect circle there. Imagine it's a circle.
Are those supposed to be centered at z0?
That too.
Okay.
There are many limitations here. Actually, the mathematics doesn't depend upon there being. Well, yeah, it does. I want them to be circles. So imagine that there are 2 circles around z0. And z0 is at the center there. Now, we're going to do a contour like this. We go all the way around. And then we get to this point here, and we go like that. And then we go around this backwards. We get to here, and we go out to here, and then we continue around. Okay, this is a closed contour then. Goes. All right. Now, what I forgot to mention is that there are some singularities. I imagine that the singularities are inside this circle and outside the outer circle. Because I've chosen the singularities, I've chosen the 2 circles so that the 2 circles enclose an annulus in which the function f of z has no singularity. And the point z is inside that annulus. Okay, well, it follows then that by Cauchy's integral theorem, that f of z is 1 over 2 pi I integral around the contour, and I'm calling this contour C12 f of c prime dz prime over z prime minus z. Yes. Okay, and this is this contour C12. And this inner circle here is C2, and this one is C1. So C12 is this joint contour. Okay, well, the first thing we do is we bring these two lines close together, and then they cancel exactly. So we can rewrite this thing as 1 over 2 pi I integral around C1 f of c prime dz prime over z prime minus z. But now the other circle is clockwise, and so if we make it counterclockwise, we get a minus sign, so it's minus 1 over 2 pi I integral around C1 f of z prime dz prime z prime minus z. Okay, so that's our formula at this point. Now the next thing we do is we say that, in fact, I'm going to make this a little bit, I'm going to use a somewhat more helpful notation. Z prime is going to be on, oh nuts, I did exactly the wrong thing. So, Z prime are the points here, Z double prime are the points there. Well, what's clear is that the magnitude of Z0 minus any point Z double prime on so Z0 minus Z double prime, which are these points out on, on C2, which is in here, this is equal to the radius of this circle, which is, say, R, and that's less than or equal to Z minus Z0, because Z is outside of that circle. Also, Z0 minus Z prime, these are the points on C1, is equal to some, in fact, I should have called this R2 and R1. This R1 is greater than or equal to Z minus Z0. Okay? Because Z prime minus Z0 is R1, and Z minus Z0 is less than that. Okay? In fact, what we have is strict inequality. It's not less than or equal to, it's strictly unequal. Okay, well, we can use these to rewrite these integrals. And so what I'm going to do is I'm going to write it this way, f of z equals, the first integral, I'm just going to insert z0 twice with different signs. And so I'm going to get 1 over 2 pi I integral around C1, this is the outer circle, f of z prime dz prime over z prime minus z0 minus z minus z0. And then the second one, first of all, we're going to absorb this minus sign into the denominator so that it's z minus z double prime. And then I'm going to this is the inner circle. And so what we've got is z minus z0 minus C double prime minus C0. So that's the basic arithmetic setting this thing up. Are there any questions?
Did you realize that he asked the question?
No, I didn't. What's the question?
I did.
I'm sorry.
It wasn't much of a question.
You get sued. That was my question, by the way.
All right. All right, so there are 5 of you who haven't asked any questions at all. All right, the next thing we do is we factorize the denominators, as we did last week. In other words, we get 1 over 2 pi I integral C1 f of z prime dz prime over z prime minus z0 times 1 minus z minus z0 over z prime minus z0. Let's see, I don't really need square brackets here. The next term is 1 over 2 pi I integral C2 f of z double prime dz double prime over z minus z0 1 minus z double prime minus z0 over z minus z0. So these are that's what our integrals look like now. Now remember, because of these inequalities, the absolute value of this ratio is less than 1, and the absolute value of this ratio is less than 1. So these things are the form 1 over 1 minus epsilon, and this is the form 1 over 1 minus epsilon, or as long as epsilon and absolute value is less than 1, we can expand that fraction as an infinite power series in epsilon with very simple coefficients, and which in fact converges absolutely and uniformly as long as the ratio is less than 1. And in that way what we get is the sum n equals 0 to infinity. And notice this is an integral over z prime. So the z minus z0 can be brought outside. And so what we get is z minus z0 to the n, 1 over 2 pi I, integral around c1. And now we just have z prime dz prime over z prime minus z0 to the n plus 1. And another power series, m equals 0 to infinity. 1 over z minus z0 to the m plus 1, whoops, 1 over 2 pi I, integral around z2, z double prime minus z0 to the m, f of z double prime dz double prime. So in the first case, we're expanding in powers of z minus z0 over z prime minus z0, and so this denominator, z prime minus z0, gets to very high powers, and we can pull out the z minus z0 in the numerator. Here, we're expanding in powers of z double prime minus z0 over z minus z0, in which case we can pull out the factors of z minus z0 in the denominator, and then we have lots of powers of z double prime minus z0 in the numerator, but of the integral. So that's where we are. Right, now these two integrals don't have z in them. And so what we can do, and they're both counterclockwise integrals, what we can do is we can collapse them into one integral just to make it a simpler formula. And we can make it, we can either collapse C1 onto C2, or C2 onto C1, or the two of them onto some circle that just lies in between. So that's the next thing that I'm going to do. And when we do that, we get the formula f of z is, well, all right, we're going to do that, but we're going to do something else. We're going to replace, we're going to set m equal to minus n minus 1 in this sum, or equivalently n equal to minus m minus 1. And when we do that, this is then z minus e0 to the minus m minus 1, but that's just z minus e0 to the n. But n runs from minus 1 to minus infinity. And so now our final formula is f of z is equal to a sum n equals minus infinity plus infinity z minus e0 to the n 1 over 2 pi r integral around this contour that we've collapsed the two contours onto, the two circles onto, f of z prime dz prime over z prime minus z0 to the n plus 1. So that's our final formula, and this is the series that's named after Laurent. Okay, and notice when we collapse onto this contour, it doesn't even have to be a circle. It can just be any contour that goes around z0 and outside of the first circle and inside the second circle. And those two circles are just such that there's no singularity between the two circles. All right, what one often does is one often rewrites this series, and one says f of z is the sum n equals minus infinity plus infinity a sub n z minus z0 to the n, and then writes a sub n equal to 1 over 2 pi I, integral around the contour f of z dz over z minus z0 to the n plus 1. Now, you can't apply Cauchy's integral formula to this because the function isn't analytic inside this contour. It's only analytic here in this region between the two circles. And that's the power of these Laurent series, namely that they work for functions that have all kinds of crazy singularities. You just have to find an annulus where you can draw two circles. All right? I feel bad that some people haven't gotten any candy. Questions? Yeah.
So where in this process does the fact that there are circles come in?
Where what?
Where you said that you need to find an annulus where you can draw two circles.
Right.
So where?
All right. The two circles allowed us to do this nice geometry. If we had arbitrary contours, we'd have to think hard.
Oh, that's got to be in the quality there.
Yeah, so you've got to have, in other words, you've got to have, see the formula has a z0 in it, so you've got a z0 somewhere, so that's some point. And then you've got these various singularities. And then you also have to figure out where is the z that you want to represent things. So, for example, if you wanted z very close to z0, you could just do the integral around here, and then you could apply Cauchy's integral formula, and all the ones in which n was negative would be 0. And so you just have a power series. But then, so that's if z were in here. On the other hand, if z is, say, here, well then you'd be encircling at least, if I'm drawing this right, this point, and maybe the geometry is such that you could have done that, and then you get z like this. Okay, so you're sort of scrunched here between this singularity and that one. It has to be smaller than that, and it has to be bigger than that one, and z has to lie in between. And if you pick a z out here, then you want to do something like this, and then if there are no more singularities out there, well, then you can draw the circle any way you want as long as you close z. So that's sort of what goes on.
So it's only valid within the annulus.
Excuse me?
It's only valid within the annulus. You pick the solution, the f of z.
The 3 or 4 of you are going to run me out of candy. Maybe you're going to have to put a limit on the amount of candy, at least for your own health and for my supply of material. So the question was what now?
The function's only valid within the annulus where there's no singular. I mean, the one that you choose where there's no singularities. The series, I guess, is only valid.
Yeah, the way you set it up is that z, the absolute value of z has to lie between some R1 and R2, and f of z has to be analytic inside this annulus. That allows you to do the geometry. Now, of course, you have some freedom because you can change what you mean by the point off z0. Point z0 is typically picked at your own convenience. So is the camera going to follow me? All right, now we have some definitions. We have this series, and one of the coefficients stands out. A sub -1 is called the residue. The residue of the function and in fact, what is this A -1? Well, A -1 of Z0, say. So A -1 of Z. See, these things depend upon Z0 as well as upon F. So A -1 of Z0 is 1 over 2 pi I integral around the contour F of Z dZ over Z minus Z0 squared. Okay, so that's called the residue. Oh, wait a minute. I thought that was wrong, and it is wrong. The point is, n is -1. -1 plus 1 is 0. And so it's just this. This is the residue. I thought that was wrong. So it's the residue then is the integral of f of z dz around z0. And of course, it's around z0 in this contour that lies in the annulus. Now, as I mentioned earlier, a function is analytic. The analytic everywhere is said to be entire. The other phrase is homomorphic. So holomorphic and entire are the same. Now,
I don't need candy, but why are we defining why are we defining something called a residue? I mean,
the reason is that
it's just a term in the series, right? I mean, the first term in the series.
it's the first
it's
the first weird term in the Laurent series. And there's something called the calculus of residues. So this thing comes up a lot when you do the calculus of residues. All right, the function f of z has an isolated singularity. At z0. If it's analytic, in a disk, some small disk around z0, but not at z0 itself. So in other words, it's analytic. Its region of analyticity is basically a disk around the point z0, but punctured. It's the disk minus the point z0. That's said to be an analytic, an isolated singularity. And f of z has a pole of order n greater than 0 at z0 if z minus z0 to the n, f of z is analytic, or is analytic at z0, which is to say is that it's differentiable around z0, remember. But z minus z0 to the n minus 1, f of z, has an isolated singularity. At z0. All right, so these are all more or less sensible definitions. Now here's something weird. Functions can have poles of infinite order, and that's called an essential singularity. And these are spooky. So if a function has an essential singularity at z0, then this series here goes all the way from minus infinity to whatever, plus infinity perhaps. But in particular, you need all these negative terms, or at least you need, not exactly every one of them, but you need an infinite set of them where n is arbitrarily large and negative. That's called an essential singularity. Now, one more definition, meromorphic. This is like holomorphic, but has isolated singularities. So a function that's entire except for analytics, except for poles, I should say. So it's entire except for poles. And in fact, I would imagine that includes the case, although I haven't checked this right now, but one of you guys sitting at a laptop can check this out. I think that if a function has an infinite number of singularities, but they don't cluster, they're just poles all over the place, then it's still meromorphic, even though it might be an infinite number of poles. Now, if the poles cluster, then we might be talking about an essential singularity. All right, example. F of z equals e to the 1 over z. This is an essential singularity, and in fact we can expand this thing very simply. This is just the sum n equals 0 to infinity 1 over n factorial 1 over z to the n. And we can rewrite that as a Laurent series by saying it's n from minus infinity to 0, 1 over absolute value of n factorial z to the n. So there you see the sum runs to minus infinity, and that's why it's an essential singularity. Now, one of the, I said these essential singularities were spooky. It's in fact true. This essential singularity is at 0. So essential singularity is equal to 0. In fact, you can show that if you take a disk of size epsilon around 0, this function approaches every complex number in that disk. In other words, you can find a z near 0 that is very close to every, in fact, you can probably find one that's equal to. If you say w is some complex number, you say w is e to the 1 over z, then you say log w is 1 over z, so you just need to say z is 1 over the natural log of w. And although we haven't really done logs in this class yet, the log of w is the natural log of the absolute value of w, which is, say, r plus I theta. In other words, w is some point in the complex plane here, distance r out, angle theta like that. Then the z that hits that is 1 over log of that plus I theta. And so this z will be inside the small disk. Well, in fact, if r is huge, okay, then 1 over z, if r is huge, then z is very small. If r is very small, then z is also very small, because when r is very small, this is like minus, it's a large negative number. What I'm puzzled about here is what about the point w equal 1, in which case z would have to equal 1. No, not 1, but something a little bigger than 1. Anyway, I'm going to have to refine this, but it's, you can see that you, within that disk, you can hit many, many points in the complex plane. Certainly any point outside of a given circle or inside of a given circle. All right, another example. What's the time? Okay. F of z equal to 1 over z plus 1. Okay. What about this? Does somebody want to guess what kind of function is this? Is it meromorphic, entire, or what? Well, I've showed you the definition, so you should be able to figure that out. I think you'll drink tea when you guys puzzle, but tell me how do you characterize this function?
It has two singularities.
Right.
What is that?
Two poles.
Well, what's the difference between a pole and singularity?
Well, a pole, it's over here. A pole of order n is if z minus z at z0 is if z minus 0 to the n is analytic, but z minus z0 to the n minus 1 f of z has an isolated singularity at z0. So that's the deal. In other words, a pole is something that's essentially 1 over z minus z0 somehow. So this has a pole at 0 and a pole at minus 1. So it's meromorphic. All right. Otherwise, it's analytic though. And we can expand it then in a Laurent series, and so let's do that. Minus infinity to plus infinity, a sub n z to the n. So then a sub n is 1 over 2 pi I integral dz z to the n. All right, let me do it in 2 steps. Okay, so that's the formula for the coefficients, and we can simplify that as saying it's 1 over 2 pi I. Whoops, I was about to write f of z, but we have f of z there. So this is simply dz over z to the n plus 2, z plus 1. So that's our formula. And now where are these singularities? There's a singularity at the origin, and then there's a singularity at minus 1. And so the natural, and where are we trying to expand this thing? Well, we're going to be looking at z less than 1 in absolute value, so we're going to take as our inner circle something arbitrarily close to the origin, and the outer circle just has to clear the point minus 1 here. So so if we were deriving this thing from scratch, we'd have these to be the 2 circles, and so our circle is just any circle that circles the origin at a finite distance away of less than 1. And now to do this integration, a cool way of, since z on this circle is going to be, it's going to have z less than 1, we can expand this thing. And so we can say this is 1 over 2 pi I integral dz z to the n plus 2. And now we have here 1 over 1 plus z is the sum minus z to the n from n equals 0 to infinity. And I should make this m so as not to conflict with that index n. All right, so what is this integral? Then a sub n, this coefficient is 1 over 2 pi I, sum m equals 0 to infinity, integral along the contour c, and it is minus 1 to the m, and it is z to the n over z to the n plus 2 dz. And remember, this is essentially just a repetition of the Fourier analysis, namely that if m is n minus 1, then this is effectively 1 over z, and we're going to get 2 pi I out of this thing. But if m is not equal to that, then we're going to have a d theta integration that's going to be e to the I n, e to the, in other words, maybe I should do this in more detail. 1 over 2 pi I minus 1 to the m, sum on m from 0 to infinity. These integrations, remember dz, if z is r e to the I theta, dz is I r e to the I theta d theta, then this thing is an integral. We've got r to the m minus n minus 1, because we get an extra r from the dz. We have an integral 0 to 2 pi d theta. We have an I from here, and we have e to the I theta from the dz. We have m of them from here, and so we have e to the I theta m minus n minus 2, and then from here plus 1. So that's the integration. And this integral will be 0. This is always an integer up here. If this is a non-zero integer, the integral is 0. That was what we found when we did Fourier analysis and so forth. If, on the other hand, this integer up here is just 0, then you get 2 pi. And so this thing then, a sub n, and the i's have canceled, and so we have a sum minus 1 to the m equals 0 to infinity, r to the m minus n minus 1 delta m n plus 1 equals 1. This cancels, this gives you m minus n minus 1, so m has to equal n plus 1. Okay, but when n equals n plus 1, this is just r to the 0, which is 1, and so this is equal to minus 1 to the n plus 1. And now for n greater than or equal to minus 1. Now why is it that n is greater than or equal to minus 1? Well, because m, the sum m, that's because m is greater than or equal to 0. And so if m is, say, 27, then n is 26. But if m is 0, n is minus 1. And so n is greater than or equal to minus 1. And so now our function then, f of z, which is 1 over z plus 1, is then the sum n equals minus 1 to infinity, minus 1 to the n plus 1, that's the base of n, z to the n. So n goes from minus 1 to infinity. This is the Laurent series for that. And you see that this converges for z. This converges for absolute value z strictly less than 1. Okay? So that's an example. What's the time? Oh, we got time. I'm absolutely astounded that there haven't been more questions asked, especially from those who haven't gotten any. it is wrapped up, so you don't need to worry about my fingers are doing all over. All right, the next topic is the calculus of residues. And the point here is that if we have a region of analyticity, and we go from one point here to another point here, then we can go this way, or we can go that way, or we can go like that, and all of those contours from Z1 to Z2, f of Z, dz, they all give the same value of the contour integral. In other words, the contour integral only depends upon the endpoints. As long as you stay within a region of analyticity, in other words, you deform the contour in a region of analyticity and you never cross a singularity, then the contour integral is a constant. And so let's consider the case where we have some contour here that does enclose some poles. Might be some out here, some in here, some out there. So, what can we do? Well, we can certainly change this contour. We can go like this. And then, in fact, we can go like that. So I've deformed the contour without changing, without going across any singularities. But now we can deform it even further. We can bring this thing in like this and go down like that, and then go here. And then we can say, well, let's bring this contour all the way down here, and then go like that. And then we've blocked off this part. And now we can just bring these two guys together. Okay, so we've gone from this contour that goes around all 4 points, we've gone to a contour. In fact, if you now shrink these guys, which way is this thing going now? It's this way and that way. So now, if we shrink it some more, we just get these lines that are parallel and infinitesimally far apart cancel, and so now we've got 4 counterclockwise integrals around the 4 points, and we can shrink them further so that they're infinitesimal circles. So in other words, the lesson is that the integral of f of z dz around some isolated singularities in a function that's otherwise analytic is the same thing as the integral of f of z around the sum of the singularities, but those are just the residues. So that means then that the integral on the contour of f of z dz is the sum k equals 1 and n of the integrals around tiny contour ck f of z dz. But those things we learned over here, these are just 2 pi I times the residue. Okay? Can you swing swing that around? So in other words, the integral around the contour is 2 pi I times the residue. In other words, I can just bring this thing around and I get 2 pi I like that. So these things are that. And so this thing, in other words, expense. This thing is 2 pi I sum k equals 1 to n k minus 1 of zk. So in other words, the contour integral of a meromorphic function around a closed contour, counterclockwise, is 2 pi I times the sum of the residues of the enclosed isolated singularities. This is called the residue theorem. And people make a big deal of this theorem, but in fact, you see, it's just a consequence of many of these other results that we discussed.
Do you just find the A's by integrating them?
Mm-hmm.
Do you just find the residues by just
Well,
performing the individual?
one way to do that is to just do the integral, but sometimes you can find the residues more simply than that. So I'm going to now give a bunch of examples, or at least a couple of examples. Well, we don't have much time. All right. So if W is a simple pole of Z, then this thing might look like this. A minus 1 of W over Z minus W plus the sum AN of W Z minus W to the N. So what I've done is I've just done the Laurent series for the case where you just have, first of all, you're doing the series around W, and the function has just a simple pole at W. Then it looks like that. Well, then the residue, A minus 1 of W, is just simply the limit Z goes to W of Z minus W times f of Z. So in other words, if you know this function and you know it has a simple pole at some place, then you can find the residue very simply. You just multiply by Z minus Z0, Z minus W in this case, and take the limit. And that's obviously easier than doing the integral around the loop and dividing by 2 pi I. And in fact, you can always get then, let's suppose a more general case. F of Z is, suppose A minus K of W over Z minus W to the K, for example, then A minus K plus 1 of W over Z minus W to the K minus 1, and then higher terms. Well, you can also you can compute all of these guys by just saying, if you say A minus K of W is the limit Z goes to W of Z minus W to K f of Z, because you'll get 0 from all the other terms. And you can pick them off one after the other in that way. So that's one way of computing. You can also do the integral. Well, I think we are kind of out of time. So I'll pick up at this point next time.